Okay, so we'll go back to where we were yesterday. If you, for those of you who were here in the room yesterday, we spoke about the application of dislocation dynamics, so typically the edge screw model 3D, to the case of fatigue crack initiation. We saw how the first crack could initiate. So just to refresh your mind, I will show you what we said yesterday. And today we'll see how it propagates. Okay, so we go to the next stage. So this is the aim of the first lecture. So this is how it works. Yesterday we said that after a very, I would say quite very precise DD simulation approach, we were able to set up a criterion for the crack to initiate, which looks like that. It means that you will have a crack at this place when a given energy will be at that place, typically when a set of multiples, so those multiples are prismatic loops, remember, those are there here, that will be swept by the dislocation here at the interface, and at one given time they will reach the interface, giving some energy at that place, and at that place you will have also some opening stress component that can come from the shape factor, so the extrusion height, let's say. This shape factor will concentrate locally the stresses, so that at that place you may have some opening component of the crack that will lead to the crack. And I said, of course, in reality it's even worse than that, because there is much more irreversibility in reality just because of oxide at the interface. Every time you make a fresh step, it should be contaminated by oxygen, and when you can, then because of that you cannot reverse the step. In my code I do reverse the step, which is, I would say, quite soft for the mechanism. We can make it better, but it will be again arbitrary rules. Here we didn't want to do that. So finally we were able to say that the number of cycles for initiation will follow such a law, which I would say maybe phenomenological, because it's a fit of the DD parameters, DD outputs, which depends on several parameters such as the loading, the average, so the mean strain you apply, the strain amplitude, the shape ratio of the grain, and so on. So you have many parameters that enter into play in the model. So it means that now we know how it depends on it. We don't know exactly the threshold. Threshold is the parameters, because this is depending on your material and many parameters. So you need to, if you want to use that relationship, you just need a point. So you just need to measure one point experimentally that will fix this threshold, and then you have your dependency. Okay? So now let's go, so because of that I say, okay, there is a crack between the pro and against nuclear. So this is where we stopped yesterday. So now let's see how the cracks will propagate. So we'll go to propagation. Propagation, so yesterday I explained how it initiates at the PSB interface, typically persistent slip bond interface. Now I'm looking for two cases. The first case will be when the crack is initiated, typically that one, it will move, and yesterday somebody nicely said that it will stop at the first microstructural barrier, what will be the grain boundary. So what is the motion of this crack toward the grain boundary? So I will show you this now. And the second part of this first lecture, I will show you what happens next when it reaches the grain boundary, like that, how it can transfer to the next grain. Okay? So these are the two parts of this first lecture. So how to introduce a crack in the DD code? So that's not a trivial thing. There are several ways to do that. We are now just using a new way. Maybe I will explain that later on. Here it was very simple. The simplest thing I think you can do. The first thing is that you should introduce some free surfaces, because the crack is a free surface, in your code. So it means that this is my DD code. You see the persistent slip bond is there. This is the free surface. Here we introduce some two free surfaces where the dislocation could go out. They could escape. Okay. And when they escape, of course, they will create steps at the surface. I will just explain in my today's lectures how we compute steps, plastic steps. So they will create steps at the surface, they will escape. And this will modify a bit the crack tip, and maybe because of that, the crack will advance or not. Or you see, we can compute that out of DD. Now the crack, the best way to do that would be to mesh that in FEM, typically to have the FEM modeling, FEM mesh of the crack. The even better way would be to use XFEM. I don't know if you know XFEM, so the generalized finite element method, where you have some non-divergent, you can accommodate divergent fields ahead of the tip. That would be the best. Here we didn't do that. We wanted to have the first order approach. What we do is that we put the crack as if it was an infinite 2D crack. So an infinite 2D crack, you have very nice analytical fields in textbook, which looks like this, where you have the mode 1, K1 This is the intensity stress factor divided by the distance to the crack times the functions f. The same for the mode 2. Mode 2, I remember, let's remind you that this is mode 1. This is the mode 2, this is the crack tip, mode 2, and mode 3 will be this. So mode 1, mode 2, mode 3, you have the 3 modes like that, which depends on such a formula. So this is what we put. We put this stress field analytically in the box. We superimpose to the DDD simulation this stress field. So it means that the dislocation will feel such things like that, very diverging at the tip here. So they will feel it and maybe they will react to that. Okay. Next feature we add, so we have the two faces, the stress field. One more feature needs to be added. The fact is that because now you have a crack, there is no more reason to put a single source as I did for the fatigue test, because here, because of the crack, you may nucleate dislocation on every SIP system, of course. There is not one single system that will accommodate. Possibly, you may have all the systems. So because of that, what we do is we introduce some Frank-Reed sources. These small segments here are sources. So we put five dislocations per slip system, so 60 new dislocation sources ahead of the crack. So somewhere here, there, we put many dislocation sources all along the crack. And we let them move. If they want to accommodate plasticity, then they will do Frank-Reed mechanism, cross-slip, whatever. They will accommodate what you apply. As we saw previously, they always do what you apply. Okay, so you get it, the three ideas? Free surfaces, stress field, and dislocation sources. Except that the code is the same as what I showed yesterday. The dislocation dynamics code is 3D as before.
So this is an additional stress field.
Well, yes, you sum up. Exactly. It's a new one, but you add in your box.
And all the R's are being evaluated from the tip of the
Yes, yeah. So you compute at each point. When, for example, if I want to compute the stress at this dislocation here, I will add, this is just a formula, so you call your formula with...
And this just gets added to the global...
Exactly. To the global and internal, yeah. To the dislocation, yes. So dislocation, applied one, and crack. So now you have three fields that you sum up, okay? Just because we deal with linear elasticity, we can sum up, okay? You can superimpose the fields. So now if we look at inside the simulation, so this is the simulation as I showed yesterday. You can see the persistence band at that place. This is where the plasticity is localized. Again, we put some zebra to see where it is localized, to visualize. It's better to see how it's deforming. This is the case where everything is the most deformed. At that stage, the crack was not introduced, so this is what I showed yesterday. You have your persistence band, and you can see that it is sheared everywhere, more or less. You see the band shear the matrix everywhere. At that place or that place, the deformation is more or less the same. Now, if you put a crack, so this is my crack, you see that here the displacement is bigger than there. So it means that the crack is introducing some extra shear at the place you put it. Like if it's normal, it's a kind of relief. It relieves the stress locally. So here you have more shear at that place, at the head, at the crack tip. Okay, but it's not so. It seems to be compatible. Okay, so let's go further. So this is I was here. I explained you this. Let's go here. Here I want to show you how the crack will cooperate with the dislocation microstructure. So this is my crack, again, in 3D. The free surface is there. This is the crack. This is the persistence band. Now this is when it is flat. Cycle number 2, 4, 6, and 7. So you can see that there is some collaboration, some let's say, interaction between the crack and the dislocation density. So here, this is what we did. Here you see the dislocation density evolution for the two slip systems that I showed yesterday. So the primary one, the secondary one. So this is a mode 2 cracking. You can see that those two more or less tend to be the same. So there is a dislocation density which are equivalent. And at that stage, so after 50 cycles, now we introduce the crack. Of course, because the crack has to be introduced after the PSB is formed. So we put it here, and we see how it goes on. And what you can see is that locally, so at that stage, if we look, it looks like that. You have something which is quite compatible. You have some plasticity which is expanding ahead of the crack. You don't have some slip dispersion. Although we put a lot of dislocation sources, right? It could have made a lot of noise and developed a microstructure, and it didn't. There is some nice, let's say, collaboration between the dislocations and the crack. So they are happy to be together, like if it was indeed a good way to introduce the crack. I don't say that this is the reality, but I say it's not stupid. This is something that is possible. Now, if I do the same but with a grain for which there is no crack, well, there is no PSB, so from the beginning here I put the crack just to check the difference. So just assume you put your crack and you cycle, okay? So you don't have your PSB and you see what happens. Things are a lot different. You have your primary slip system, which is like that. All the other systems activate, not much the systems which are not loaded in fatigue, but two of them here are important. The deviate one still here, and some over here also is quite important. So this is very different from the PSB. We see that we don't have the same density evolution. And if you look at the dislocation microstructure, it's very much different. Now you have something which is totally located ahead of the crack. You have a kind of, it's similar to what we saw yesterday with the MD simulation. Remember, in MD we saw this big dislocation spaghetti ahead of the tips. It looks like that. You have these big spaghettis which are developed ahead of the tip in this virgin material. So it's normal. It's indeed similar to what we did with MD. So here you can see that it is not easy for the crack to advance because there will be this hardening here, this forest microstructure that will be very complicated to interact with the crack. So this is something different. So it means that a crack in fatigue would be very much different from a crack in a non-deformed grain. See, there's very much difference between the two. So from that now we can compute the crack advance. So how fast your crack could advance. That's the first case, of course, after with the PSB, you have your PSB, you put the crack. Is it, we saw that this could be compatible. Is this increasing the crack advance or decreasing the crack advance? So to do that, we compute what people call the crack tip slip displacement, CTSD. So it means that at the tip of the crack, we compute the displacement field due to the dislocations, and we see if it's bigger or smaller, how it moves with the cycling. So this is plot here for different stage of a given cycle, okay? Here you have the initial position of the crack. At that stage, you can see that the crack advances a lot, not a lot, a little bit. You see this is the microns, a little bit. And then when you unload, it is reversed. So a part of it, a big part of it has been totally removed. Then you negatively load, you can see that it is shrinked, and then again it's back. So it means it's highly reversible slip, okay? But again, because of the same assumption I explained yesterday, in reality, this could not happen. In reality, when you have your crack, it's like a fresh step that you create in your sample. You will have some oxide coming there that will contaminate the surface. Then when you unload, those oxides will be entered in your materials, and this will decrease a lot the cohesion stress of your material. So it means that in practice, these two steps, for example, are totally impossible. It's impossible to completely remove the crack, okay? So this is something that we should keep in mind, but in our model, this is, I would say, too kind for the material, too nice for the material, okay? Now, this is the slide I thought was before. So this is something that we also investigated. We say, okay, we know that the crack will be at the interface between the bond and the matrix, but the question was, do we put it at this place or at the other place of the bond? You have, the bond is like this, you can put inside or outside the PSB, so either upper or below. We saw experimentally that this one looks to be the right place. This is what we call the obtuse angle, so we can see it here. This is the obtuse angle, and this is the other side. This is what we call the acute angle, because here you have this acute angle, which is not favorable. And if we do the simulations, our DD simulations, we saw that if we put it on that place here, or in the center or in the right, so here I think I was confused. Here we have the free position, either on the right, which is here, either in the center of the persistent slip bond, or in the left, the persistent slip bond. So if we put it on the right, we saw that you have high stress concentration, high slip reversibility, as I showed before, and the crack tip remains sharp. So it means that it is possible for the crack to advance very easily in that configuration. If you put it in the middle of the bond, here you don't see much, but all the red colors indicate the dislocation densities. The PSB thicken. You have something which is thickening your persistent slip bonds. So you have a big amount of slip dispersion. So it will no more move in the mode 2 regime. It will be totally dispersed. And this will blunt the tip. So it means that the tip is no more sharp. It will be blunt. So it means that typically that it's not a good collaboration between the two. And on top of it, now if you put on top, you have still the high reversibility as you can get on the bottom here. You have few slip dispersion, but the crack tip slip displacement ahead of the tip is lower than in that case. So thanks to those three analyses, we think that the best position for the crack would be that place, because at that place, the crack tip slip displacement is the highest. So this is the most, let's say, collaborative way to introduce a crack. But this one also is possible in the second order, and this typically is impossible. Okay? So those are the three possibilities. Now, well, yeah, so this is what I conclude here. Most favorable, not favorable, and less favorable.
This classification is for the propagation of the
It's for the, yes, we are just looking now for the crack, how it advances to the grain boundary. This is,
where the nucleate is still, what is most favorable for crack nucleation?
So yesterday we said that it will be at that place because of the local energy and stress. You see?
But of these three, whether it will be to the left or it will be to the right, that we cannot.
That we cannot tell, but typically we have an idea that if we, according to what we said yesterday, we said that the crack will open because of the stress concentrators, stress concentration due to the load. Since you are loading equiaxially on the surface, the concentration will not be high as high. Here, the stress concentration will be higher than there. If you have some extrusion like this, here you will have higher stress concentration than here. So this is why I think that this one also is most favorable. But even if you put it there, and actually in your experiment you may have some also crack on the other side. Even if you put it there, it's not so bad. You may have a crack there. Both are similar, I would say. In my code, be careful of that. In the code here, we don't have this stress concentration. Remember, we don't mesh everything here to look at the stress concentration. So this is something we don't have. We just do it roughly, I would say. Okay. So now that we know the crack would advance at this place here, so on the acute, obtuse place compared to the percent slip bands, we were investigating the position of the crack compared to the grain boundary. So this is the grain boundary, which is here, this first microstructural barrier, as I said. So this is the grain boundary. The dislocation the crack is here, is long, now is there. Okay, this could be different. What is the difference between this position and that position? Just to see if the crack propagation is always the same during the grain. Because of course in my DD simulations, the crack will advance at each cycle something like 5 nanometers. So I cannot run 2,000 cycles to see the crack going toward the boundary. It's impossible with my DD code. So I need to put it by hand at several positions and see if the crack tip slip displacement, so the velocity of the crack, is modified or not by the presence of the grain. Okay, so this is what we did. So first we put it here, and then we put it there, and we compute the crack tip slip displacement as a function of the distance to the grain boundary. So this distance here, okay, or this distance there. And you can see clearly on the picture here, because this is for the same grain size, that when you have it here, the dislocation are nucleated ahead of the crack and they propagate in the persistent slip bands. So this is nice for the material. When you are close to this accommodates the plasticity. When you are close to the grain boundary, then there is no more space to accommodate the plasticity. You are loading, you want to accommodate your 10 to minus 3 plasticity. It has to be accommodated here, and there is not enough space to accommodate that. So because of that, you have a lot of slip dispersion. Dislocation cross slip and go everywhere. All the slip systems are now activated, you see. So you have some large dispersion like that will slow down your crack. The crack will be slow, actually it will blunt the tip and slow down the crack advance. Okay, this is the process. This is the main idea. So here you have typically a big interaction with the distance to the grain boundary. So the crack tip displacement, when you are very close to the boundary, is close to 0. You see, you have it slows down a lot like that. And the velocities at which it slows down depends on the grain size. If you have a smaller grain, you can see the slip displacement, which is here, okay? The slip displacement is going down, is less in the small grain than in the big grain. So it means that the small grain will be cracked more easily than the big grains. The small grains will be easier to crack than the big grains because of that, just because the slip displacement here is less than there. There you have a huge slip displacement, so a huge blunting of the tip, and it will stop your crack. Here it will not stop the crack as easily because of the small grain. Okay? And from that we were able to fit that kind of curve here, which depends on the diameter. Okay? The fitting curves are the dot line here, like this and like that. And if you fit that with exponential laws, it looks like this. You have the crack tip slip displacement versus the diameter of the grain, which follows such a law, like that. This is nice for people from damage mechanics, because this is typically the crack advance. Here we have the crack advance, so you know the dA over dN that people are plotting in log term. This is exactly what they are looking for. And here we found something which is an exponential term. Okay, so I concluded here. The crack advance is easier in small grain. So this is the main thing to retain on that, okay? Because of this X-form GIAN, we can see it here for the smallest grain, this thing. So now if you plot this advance in a log scale, it will look like that. This is what I showed yesterday. This was the number of cycles before the first crack initiate, and here you have different diameters, 10, 20, and 30 microns diameters. Number of cycles, plastic strain amplitude. We found that this follows the number of cycles reversed of the plastic strain amplitude, like this. Now if you add, or you superimpose to that the propagation stage of the crack, it follows this exponential law, like that. You can assume that this is similar to the propagation velocity of your crack. And this looks like this. You have something which, again, depends a bit on the diameters. Those three diameters are plotted there. And you have something which is slowing down for this amount of deformation, like that, okay? So this is the crack advance, like this, which depends on the grain size and the plastic strain amplitude. Okay? So here the conclusion is the crack propagation slows down close to the grain boundary. This was well known, but here we have the demonstration using discrete dislocation dynamics. Okay, do you get the idea here? So this is what we did. We put the crack, and we compute the crack tick slip displacement to check how fast it could go. Then, the crack now has reached the boundary. So it is at the boundary. It is here, for example. And I want to know, can it propagate to the next or not, next grain? So we want to look at that in a kind of polycrystalline model. Now we want to check what happens in the next grain. So here there are two possibilities for a crack to transfer to the next grain. Either you have your crack, which is like here, as we saw here, and then going through the interface like here. This is not, I think, what we will expect in our case. In our case, because we know that the crack comes from the fatigue persistent slip bond at the surface, we better think that the crack will be first in that grain, and then it will nucleate some persistent slip bond in that grain that will create a new crack here. It's not a crack crossing the interface here. It's more like let's say a collaborative effect of the crack stress field on the next grain in the fatigue loading that will generate some persistent slip bond here that will further lead to a crack and see how it propagates. It's what we call indirect mode. I don't know if I am clear. You see, the indirect mode means that you have first a crack here, and then because of the crack field plus the fatigue field, you will have a new crack appearing there, which is not the crack transferring at the interface. It's a new crack which is loaded there, which may explain this change of slip. So we'll see that mode. So this is what we are investigating, this indirect crack propagation. So this is the load, this is what we do. So first we fatigue the samples without the crack. So this is the grain. So the code is still a single crystal code here. We have a polycrystalline version of the code. I will show you that later on, because many of you I know are interested in the twin boundaries or grain boundaries. So I will show you what we can do today in the limit in the chapter regarding the limits of DD simulation. Here it's a single crystalline version of the code. So it means that we are dealing with that grain. This is the simulation box. And we assume that there is another grain here with a crack inside. So what we do, we can see the movie again. We load with no crack. The crack is not there. And then we put the crack, and we see what happens. So when we load without the crack, a persistent slip bond will form. Here you see the bond. And then when the crack is there, you will see if this changes or not the bond which is developed in the next grain. Okay? So this is the idea. So here, the big problem, like in your problematic you were asking me, as soon as you deal with grain boundaries, you have thousands of possibilities. Because you have a grain, and you have a neighbor grain, and then you need to check all the possible misorientations between the two. Yesterday we saw a very nice large angle boundary in TM, you see, so this is typically this. We need to investigate all the possibilities for the two grains to coexist. This is impossible to do, okay? You will spend your whole life on that. It's much too complicated. Anyway, so we had investigated a few of them. When I say we, by the way, it is Christophe Després, again, the leader of that study. So what he did is that he defined three angles, what we call the tilt angle here, okay? It's in the surface here. It gives the angles between the crack. I don't know if you see clearly the crack plane, which is here, and the persistent slip bonds, where the persistent slip bonds want to form the next grain. Then there is a twist angle, which will be the rotation in the plane like that, and then a theta angle, that will be the angle between the Burger's vector of the one grain and the next one. So you have three angles, like Euler angles, to describe the orientation between one grain and the next. Okay? So we will change a few of those angles and see what happens. So I will not show you all the possibilities because I told you it's too much, but I will show you a few of them so that you will get an idea of the mechanism. So here typically the tilt is minus 18 degrees. Okay? Here we can see two things. First, the crack you can see that is here, and you can see the persistent slip bond which is ahead of the crack, like that. So it means that because of the crack stress field, it seems that the persistent slip bond has formed at that exact intersection with the crack in the next grain. So there is an effect of the crack on the location, at least, of the bond in the next grain. Okay. And if you zoom on this thing, you can see that it is indeed made of slip bonds like that. This is the crack slip plane. It's hard to see in 3D, right? We should have the 3D view rotate to look at it, but you see the slip plane like that, and you can see that it is not thick, not very thick. Everything is concentrated. So here is something which is very bad for the material. It will highly localize. In other words, this is a very fast crack transfer. In that orientation, the crack will be easy to move and to nucleate again here and to create a new crack. So you will have a very fast process for cracking. And you can see in that region that the dislocation density evolves quite fast, and the others are not moving fast, so it means that it is really localization of plasticity. So I would say that this is nefast for the material. It's very fast damage process. And in some other case, it's totally different. This is the case here for minus 35 degrees. You see the same thing, so we put the crack and we see what happens. And now you have a huge slip dispersion here. The slip is no more concentrated ahead of the crack. It is located everywhere in the grain boundary like that. And you can see a very, very big slip dispersion here. And you can see that the dislocation density is not like that. It's not something which is increasing and localizing. It's more like this process, and you have secondary slip systems which are also developing and so on. So this is totally different, and this will stop your crack. The crack then, in that case, will not be able to move fast. Okay? So you can see that between that case and that case, the mechanical response will be totally different. Okay? This is very fast crack propagation. The crack is stopped here. To better illustrate that, I will show you also two situations where we compare the mechanism. So here I want you to be focused on what I explained here, because you have many things to understand on this graph. So for example, here I want to show you how the crack can cooperate with the initial dislocation microstructure. What are we doing here? Here we start, so listen to that, we start the blue curves here with a simulation without any crack. We don't have any crack, like I did before, so we built the persistent slip bond. So this is what we do here. So this is the irreversibility parameters I showed yesterday. This is the same curve as yesterday. We go up to 20 cycles. At that place, so this is what we have here, no crack. So we built this bond here. This bond is formed. Okay? Now, at that stage here, we introduce a crack. We put the crack here. This is here. This is the red curve. And we see what happens on this irreversibility in this grain. And you see that it is even worse. You have more steps on the surface, and you can see that the irreversibility parameters increase much more. Okay? So there is a cooperative motion of this crack here with the persistent slip bond. They cooperate. Now, if I put the crack from the beginning in this green simulation, from the beginning I put the crack and I do the same, then I have a similar persistent slip bond formed at the same place, and the rate here is very similar to that rate there. So it means that the crack imposes the rate of extrusion. This is the extrusion rate, right? This is the irreversible parameters that we computed yesterday. So the crack imposes the irreversibility rate in your next grain. This is for that case. In another case, it's even worse. Here, same idea. Three, the blue, the red, and the green. The blue, we cycle a lot, like this. We build this persistent slip bond. You can see it here nicely. Now we put the crack. The crack is put at the same place as decided before, with another angle. This is another angle, so it's a little bit different. And what do you see here? you see that there is a huge extrusion which is developed faster than that rate here. But the location has nothing to do with the primary one. So it means that you start to cycle. We said that like this. First you cycle, you build this person slip bond here in that plane. Then you put your crack. This person slip bond is more or less destroyed. We don't care that there was an absent slip bond here. And the new one forms there. And the rate at which this will grow is this huge rate here. If you put the crack from the beginning, you see exactly the same structure, and the rate is similar. So in that case, you see that the extrusion rate is imposed by the crack, as here, but also the orientation. So the crack can impose its own slip plane for the persistent slip bond. So the crack has a huge power on fatigue. You see, if you didn't have the crack, you would get this. Because of the crack, you get that. This is very important. So you can see that the crack stress field totally modify locally the stress state in your grain. And the persistent slip bond forms in other places than expected. Okay, that's the main conclusion on that. Okay, I hope I didn't lose you. I think it's quite complicated now. We are in that's the latest result we did on that. So the conclusion on this study here was the following: if we compute the irreversible parameters with a crack and without a crack, so this is the ratio with crack and without crack. This is what we can compute. This is the evolution of this ratio depending on the diameter and the position of the crack, like this. So we have several possibilities. We have some places where, because of the crack advance is slowed down. So it means that the crack is limited because of this orientation. In some other case, it will increase the irreversibility. So yes, it will speed up the reversibility like this. So it means in that case, it will be nefast. So, and this here was not investigated for all the possible orientation. This was only for this tilt angle and changing the twist angle. This is the twist angle that we modify. You could do the same if you have time with all the other tilt angle, and you can change theta, and so you have many other parameters to investigate. But this is just to tell you that there is a difference in mechanism. Some of them, this is one, so in one you have the same evolution rate. Some of one is delaying your crack advance. Some are increasing your crack advance. Okay, that's the idea. So the crack plays a big role in fatigue development in the next grain, not only in your primary grain, but also in the next grain. Is it okay with this? So this set of simulations, I want to remind you where it's coming from. This was done by my colleague. I gave his name many times. This is Christophe Desprez here with Christian Robertson. So Christophe Desprez is the one who did most of the simulation during his PhD. This was his PhD there. So it led to several papers that, if you're interested in fatigue, you may have a look to. Typically, we love FilmMag. FilmMag is maybe you don't have access to FilmMag because this is not quite well known. Do you have access to philosophical magazine? Yes, you do. Okay, so you should have a look to that. So first, we saw that the dislocation can organize into persistent slip bond. This is what I showed yesterday. This is published in 2004. Then we explained how you have this localization at the surface, 2006. I also did something on precipitates. This was with another student. This I will show today when we speak about the boundary conditions for the precipitates, because some of you said that you are interested in the precipitate effect. So I will show you that. But first, I need to explain how we introduce precipitate in the DD. And then, recently, those are very much more recent. We do that with Prasa Reddy, that is a student here from Kalpakam. Okay, it's somebody, a colleague of you. And this was for the crack in the first grain and the crack to the next grain. Okay. So that was the conclusion for this talk. And just to keep on some funny characters things. This is what was published, so again in French, let's say, newspapers. 1970, the president said, you don't have any risk. You see, this was a nuclear power plant problematic, remember? In 80, they said, nearly no risk. And 19, now they say, with some chance, we may be safe. Okay, so things are not solved today in fatigue, even for such a very important problem as in nuclear power plant. I would say that a lot of things remain to be done. Okay, so I will stop here. I think for this thing, because the next will be about the multi-scale modeling. So let's stop it here. Maybe not here, but more or less here. And if you have questions, please ask me any question. Yes. Yeah, yes. So you mean with the crack? Or, yeah. So when we put this, typically, when we put that at the interface, the dislocation, there is no possibility for them to cross. Okay, so it's like just a hard obstacle interface. So we don't care of the plastic displacement at that place. We don't match anything. We don't. It's very simple. As I told you, this is simple. We can do a lot better, but I think the result will be the same, except that we'll spend 1 month calculation in place of 1 week. But here, what we say is at the interface, dislocation stop, as you can see here. They stop and they do not create steps. There is no splitting of dislocation in the grain boundaries. We don't take that into account. Yes, I agree. I completely agree. But this, for that, we should get a polycrystalline version of the code. And this, we have it, but this is a project we have. I have a student starting on that. The code is ready for that. The student is not ready, so he's still learning that. I hope we will do it very soon. But we did some investigation, but not at the stage to have the fatigue. But we can do that, yes, and that's something interesting, yes. To put really two misorientations and to fatigue the two, and to have the two slip system. It could be very interesting to have the two persistent slip bond forming, and maybe at one stage, one persistent slip bond will impose the rate for the second one, like the crack. This would be funny to do. But again, we will not have the crack. The crack you need to introduce by hand, because DD cannot take care of the decohesion of the atomic planes. This is not something which comes from DD. Okay. So in any case, you need to impose your crack by yourself. DD is not this is not an ab initio tool. It cannot do everything. So you have to put a lot of rules locally inside, what I call local rules, and the crack is typically one of them. You have to put some local ingredients to make it work and to compensate the lacking that we don't have. All what is not elasticity, we need to introduce. Yes, Prita? Yes, yes. The stuck. What do you mean stuck for the?
Right. So there is no other than the orientation change.
Mm-hmm.
Is there a width into the boundary as well?
What? The boundary? Vector?
Do you give the boundary
Yes.
a width?
This one?
And you model that as some equivalent region?
No.
Right? That's
No.
just a short change.
Yes, it's very simple one. Actually, it's the same simulation as what I showed yesterday. It means that this is my grain box, so it's an hexagonal grain, let's say. And so dislocation cannot move through the boundary, but as simple as that. We don't put much more things like that, except that here there is another stress field, which is outside your box, let's say. It's like typically this shape, we don't account for. We don't care that this is hexagonal, spherical, whatever. This is, we put just the stress field corresponding to that crack in that grain here. Okay, and at the interface, dislocation do what they want. Of course, because of the crack tip fields, they may move away a bit, but that's it. There is no other things. You can see the crack.
The crack is as long as the boundary.
Yes. We assume that it has crossed the whole boundary. It was the first step. You see, with the previous study. First, we assume that first it cracks the full PSB. Then it is at the bottom. You can see that it has reached the bottom. And now we assume what happens next. Yeah, that's our assumption. Again, it's an assumption. I tell you, I cannot do the real case, which is there's too many cases. Exactly. Yes.
Half a dozen cases.
Exactly. Yes. So we selected this study. This is. I am not aware of there. We have a few pictures. You see, I showed you a few pictures of this kind of thing, like this. But we don't have the stress state on that. Yes. Yes, sure. Yeah. Yeah, I'm sure there is some. Yeah, I'm sure there is some. The thing is that we should know exactly the loading conditions in that stage, not only pictures. That's the point. If you want to do the same, but this I would be happy to have a set of data that we can try to reproduce. Yes, sure. Yeah. Yes, that's very important. Yes. We just so here typically if we speak about that one. So here we do the simulation without a crack, and just at that stage, so we stop the code here, and at that stage we say now let's put a stress field corresponding to a crack. So we just add at that moment the stress due to the presence of a crack inside the simulation box. You see, The stress, of course, be careful, it's depending on the loading because it's plus and minus. You have some cycling effect because your stress tensor is cycles. So it's not a constant stress, right? It's a cycle stress, which is just increased by the sharp tip of the crack. Okay. So we put the stress field at that stage here and see what it gives on the structure. But again, this is not meshed by FEM. This is just an analytical expression of a 2D crack tip as if it was an infinite crack, infinite and planar crack. This could be a change. This could be modified. Today we are working on that with XFEM, with a generalized finite element method, in order to let the crack appear where it wants. You see, and that I think will be nice. So you will do your crack and let it move as it wants in FEM. But this requires some very fine mesh locally to do that. So it's quite complicated, and we are working on that now. Initially, here it was like yesterday, only a single source was enough, you see. Here a single source was enough to develop the person slip bond, that grain. And then because of the crack, we put the sources here now. Now we have the sources, and we see how it propagates, okay? Because we know that for the fatigue, a single source is enough. So we put the single source, accommodating what you apply. But you can put the 12 if you want. But then they will not move, actually. They will just be totally reversible. They move up and down, and they don't care. So we put a single source, it leads to that. Here we put the crack plus the sources, and it leads to this. Okay? This is the idea. Yes. Crack propagation is faster in smaller grains. So this was the conclusion of the first study here. Yeah, you can see in this law here. You can have it because of the diameter of the grain. The plastic strain? What do you mean the plastic strain is less? Yeah, that's true, but the grain is small, so it means that the velocities at which it will reach the grain is faster. So it means that actually, if you normalize your crack tip slip displacement by the grain size, it follows such a law, and here you will see that it is faster for the smaller grain than for the bigger grain. Oh, previous slide, yeah. Plastic strain and grain size. I have something like that. This one, yeah. So this was but this one was for the fatigue itself. Okay, this was for the crack propagation. No, the crack initiation. So this is what we said yesterday. Just to show you that in literature, you many times you have this kind of curve, which is first square root dependence. So if you plot it here, it will be somewhere down there, and then you have something which is like that when you have your crack. So this transforms into that from the PSV to the crack. Okay, that's the idea. So this is not for the crack. Okay, this is for the persistence bond itself. For the crack, it's no more depending on squared. It's like that. It's the exponential term. So there is something like that. Okay. Yes, we assume. Yes, that's true. I don't know. How is just because the slip dispersion is less. So this is just our conclusion. Just because when your crack is close to a small grain boundary, then the slip dispersion remains more or less confined, so the crack will still advance. In the big grain, the crack dispersion, slip dispersion will occur very heavily. This will slow down your crack. So your crack will slow down in big grains. In small grain, it will not. It will the interface. So this will happen everywhere, actually, on all the sides of the grain, not only on this direction. In reality, here it was a 2D infinite crack. So I was only investigating this side of the crack and the grain. But I agree that in the case of, how do you call this, a disc crack or penny-shaped crack, this happens on all the sides. Okay, but then the stress field is not the same. You need to change the stress field. This we didn't do. We put an infinitely long crack here. Again, this is I would call it a primary study on crack. I think this is one of the few that exists in DD. You can do better, and I think you are young. You could tackle down much more complicated model, I guess. Okay. This is our just first investigation. Yes. Yes, sure. Yeah. With the tilt angles and so on, this is the misorientation there, yes. Yeah. This, the disorientation between the two grains gives you the orientations of the slip systems compared, it was not here, from one grain to the next. This one here. We just define the two orientations by those three parameters. You see, that's those three angles. So those are defined between the blue is the persistent slip bond in one grain, and the second will be the crack in the next grain. So we define these two planes, and from those two planes we can define three angles to orientate one plane to the next. Okay. In other words, that would be the persistent slip bond that you would get in a grain. Yes, and then here we put the crack in the next grain to. There's no other word. I already said it. You see, so you have your persistent slip bond and your crack, and to define one compared to the next one, you should define three angles, Euler angles typically. So the tilt, the twist, and the theta angle. Okay, so those are the three that you get here. Yes, but according not only to the loading, but also with the crack. You see, this was the conclusion. If I go back, maybe I was a bit fast. I don't know. This is what I show you here. I mean that here maybe, well, let's take that one. Here the persistent slip bond wants to form at that place, and the crack will also enforce the same motion. Okay. Here the persistent would like also to form in that place, but it cannot because of the crack. So it forms in another plane. Okay. So the planes, we don't put it ab initio. We don't force the dislocation to go in a plane. They go where they want. Okay. So they developed. Here what we put is all the sources in front of the crack, and we let him do, and we can see that either it does this or it's split. Okay. Here it was not enforced. This is just an outcome of DD. We let them do what they want. Okay. Could do tilt? What do you mean tilt?
If the stress fields are not of different size, they would actually tend to.
For the prismatic loops. Yes, true, correct.
So how is this happening? Prismatic loops are traveling.
Yeah, but actually, we don't see. Maybe this one is not the best example. Maybe this one is better. I would say that here, for example, where is it? Yes, here. This is you see, we load in fatigue. This is exactly what I showed yesterday. You can see your persistent slip bond here, the blue plane, and this is the extrusion here. This extrusion follows exactly the principle as yesterday. In that plane, I'm sure you have some channels leading to extrusion at the surface. We see it clearly maybe in the movie that I showed before. When I think there is a movie here. You see the extrusion here. You can see the extrusion is forming, and this is just because of these prismatic loops coming out at the surface, and this creates this extrusion. Okay, we don't put it ab initio. It's also something which is generated by the code itself because of the vein structure and interaction, as I explained yesterday. You will have this helicoidal dislocation or these prismatic loops, and when they are swept by the dislocation at the interface where the strain is localized, they can reach the surface. For the loop, so this is what we explained yesterday a bit. We will do the exercise. I think with pneumodisc, I think we will play with that. Yesterday I had this question already. So it means that if you assume that you have a highly mobile dislocation in a plane, like that, this is my dislocation in a plane, which is mobile very easily. So this is the interface between the persistent slip bond and let's say the matrix. This is the PSB and this is the matrix. On top of the plane, if you put a small prismatic loop, for example, the prismatic loop will have to be, this is the Burgers vector, okay? It has to be something like that. That's a prismatic loops like this. Just because of the local interactions between the dislocations and the prismatic loops, here you will have a stress that will be a lot higher than there, although this is negative, okay? Will be opposite sign because I agree, the sign of the loop is opposed. So here and there, the force will be opposed. The same for this guy. But this guy and these guys will be, let's say, at the same distance toward the loop. So those will compensate, more or less. This will be higher. So because of this higher stress, it will move. Okay? This is the idea. There is what I call a gradient. Since you have a gradient of stress between the top and the bottom, then the biggest one will drag the whole. You see, this is the mechanism. You will do that with pneumodisc to check what I explained. It will be even clearer because in pneumodisc we are able to visualize the force. So you will see that the force are higher a lot below, and because of that, the dislocation, the loop could be dragged by the dislocation. This will be one of the exercises we'll do on Monday. or Tuesday, I don't know, but it's a part of the exercise I give, okay? So if it interests you, you will check that. But, as I said yesterday, it will not drag the dislocation up to the surface in one shot. It's not like that. Usually, it drags a bit and it detaches. So the dislocation finally this gas will have been swept a bit, like this, at that place, and the dislocation escapes. So you need another one to move it further and further. So this takes time for the loops to reach the surface. It's not a single shot. You take your dislocation, you move to the surface, you cycle again, you will take another shot. No. It's not like that. Every time dislocation moves, they slightly move a little bit, those dislocations. Okay, because they are going too fast, actually. So since they go too fast, the loop cannot follow. And this is very, very famous. There is a nice study from Bacon on that also, David Bacon in England, who explained that indeed there is a velocity effect of this dislocation loop interaction. This I did not know before we did that, but indeed it has been demonstrated in the molecular dynamics simulations. Okay. Any other question? Yes? Yes, dislocation loops. Yes. Oh, no, loops of Frank-Reed sources.
So when you choose like some 5 dislocations per series.
Exactly, yeah.
How you are defining that?
No, this I don't know. It's totally, you can choose another number. This is not a magic number. It was just enough dislocation to accommodate. The crack was so big that we put at least 5 all along. We have all along the crack. I don't remember if it was randomly spread. I don't think so. I think they are all aligned, all centered in the same line. And at a given point, you take each system, you put 2 or 5 dislocations all along the line like that. No, it was totally artificially introduced. I agree. This is controversial. You can do better. The ideal case, yesterday, I think I spoke with some of you a few days ago. The ideal case for me, when you do the simulation, maybe I will put that in the conclusion, is always to start with a realistic configuration network. As Professor Sundararaman may know and tells, dislocation in reality, they are not pinned dislocation sources as we do in the code. This is totally artificial. This is a purely numerical tool, this Frank-Reed mechanism. In reality, dislocations, by the way, I should ask you the question, do you know what is the initial dislocation source in your box, in your real material? Do you know how they look like? If I look in material, like we have the beautiful picture from Professor Sundararaman in TM, what is the dislocation initial state? How are they? What do you think? Do you think you have dislocation pinned and they can act like Frank-Reed source? No, this could not happen. The first reason is that the dislocation could not be pinned in a medium. This is impossible. They are always a junction with another gas or at the surface, or you see, okay. It's impossible to have this thing. So these things we put is totally artificial, so we don't like it much. So if you want to have a realistic structure, so a bit better than my sources I put, would be to, this is a thing I suggest to my students, you put a few sources, you pull on it very fast, so that you develop a large dislocation structure, then you remove your loading, your dislocation collapse, and this creates some network. Automatically you will get a network. And at the place you had a source, so you have your network. This is an advice I would give you if you want to do realistic simulation. Then your dislocation initially was a source. It creates some network because of this mechanism. So you have many loops emitted. It's very complicated, so you have junction everywhere, you have many things. You let them collapse after this. So this creates some very nice network like this. Of course, it will be still pinned at this place. To remove those pinning points is very easy because initially this dislocation was oriented that way. You just need to close it now. You close it and you let it relax again. And then you will have a nice skeleton. This skeleton has a name. We call it the Frank network. And this skeleton is physical, I think. It's something which is balanced energetically. And it's something that you can use as a starting point of any DD simulation. It's more realistic. So this is one way, I think, to do it with the computer. You push, so you have a huge density, you relax, you close your loop to be sure you don't have this point anymore, and then you use that as a starting point for any simulation. It means that in my crack, if I do that, typically, ahead of the track, I will always have end of dislocation to accommodate the plasticity I want, so it will automatically, locally, generate Frank-Reed sources and so on. Okay. Automatically, this will be done. The thing is that we don't do that because it takes time. So usually we are too lazy to do this, so we prefer to put those Frank-Reed sources. But I agree that this is not correct. It's not very... Nowadays that we have beautiful computers, we could do better, and I think we should do such a trick. I didn't see anybody doing that, actually, but we should do that, definitely. Is it clear like that? Okay. I think we can stop here.